Hi, I'm Abhinav and I'm a grad student at Stony Brook University. Today I will be presenting a paper on stress testing autonomous racing overtaking maneuvers with RRT. This work is done in collaboration with Stanley Park from Stony Brook University and Juanes Betts, Hongre and Rahul Mangaram from University of Pennsylvania. In the context of autonomy, trust and safety is of utmost importance. With this work, we propose an approach to stress test such systems based on the rapidly exploring random tree algorithm. We focus our work in the field of autonomous racing overtaking maneuvers, but is generalizable to any autonomous system. Motivation. The motivation for our project came from the prestigious Indie Simulation Challenge, with multiple universities globally taking part in this for over $1 million prize. And we still had 12 out of the 16 cars crash and were disqualified. Overtaking maneuvers are difficult to plan because the safety of the maneuver depends on the future actions of the opponent, the interaction between the vehicles, different topological constraints at each track segment, and the current observance of the vehicle dynamic limits. The testing for autonomous racing, which is a multi-agent system, isn't exhaustive nor it is efficient. Our work tries to devise an improved testing method. Contributions. Our work contributes by firstly describing an adversarial agent perturbation and objective space. Then we devise an RT-based strategy to search over a well-defined objective space using the perturbations in order to search for collision scenarios efficiently for an autonomous racing platform. We also provide an evaluation of the performance of the autonomy through quantitative failure coverage metrics by clustering the areas of tracks where collisions happened majorly. The planners that we tested upon. We tested it on 5 different and well-reputed controllers and have found up to 5x more collisions than a random strategy. These controllers included first, the gap follower planner, which steers the vehicle to follow the largest gap in the LiDAR scans. Secondly, the disparity extender planner, which is an extension of the gap follower and finds the largest difference in consecutive LiDAR scans and follows the disparities. We use the Frene planner, which select goal coordinates in the Frene frame of the racetrack and generate multiple trajectories to follow race line and choose the best one by avoiding obstacles. Then we experimented on the graph planner, which generates a graph covering the racetrack where the nodes of the graph are vehicle poses and edges are generated similar to those in the Frene planner. Finally, we experimented on a modified pure pursuit planner, which tries to follow the optimal race line. And once it finds an opportunity to overtake, it switches lanes and follows that lane until it overtakes in a similar fashion. Our test generation method fits into a larger autonomy design and verification process. After the developer or tester provides a specific scenario and environment setup along with the path planner and the controller, our method then stress tests the scenario by finding errors due to the adversarial agent interactions. System setup. Our system setup, we use an environment which is a deterministic F1/10th environment based on an open AI gem, and the simulations are stepped simultaneously. All randomness is seeded, and all experiments can be recreated while providing support for multiple vehicle instances. We use 2 cars, an ego vehicle and an opponent vehicle, and a fixed start position for both the cars. We use the Red Bull ring map, which is located at Spielberg, Australia. And this is at the 1/10th version of the actual map. Objective space. We define an objective space as a projection of the state space into a more observable and a testable dimension space. In the context of autonomous racing, we have a huge state space, defining the pose of the two vehicles and the environment also around it. And we project it down to the following 2 dimensions. First is the percentage of the track completed by the ego vehicle. This goes from 0 to 100. And percentage of the opponent vehicle ahead of the ego vehicle. This goes from -5 to 5. Anything below -5 or greater than 5, we discard it. The objective space is our unexplored space, and we would be using the objective space as a search space for the RRT algorithm to look for collisions. The next question is, how do we generate different scenarios in a deterministic controller behavior? The answer is to use adversarial perturbations. These perturbations are nothing but slight modifications from the opponent controller's original behavior in order to create multiple scenarios and see how does our ego controller react to such deviations. Perturbations could mean like increasing or decreasing the speed, increasing or decreasing the steering angle, deviating laterally from the current pose, and many more. It depends on the domain. For our experiments, we just use two perturbations of either increasing the speed by 10% or decreasing the speed by 10%. Now let's talk about the RRT algorithm. We try to use the concept of motion planning in order to test a system over the objective space. In the same way, a robot searches over an unexplored room, we could have an observational objective space for a cyber physical system, which in this case is the autonomous racing platform, and try to explore multiple scenarios in that search space. One of the famous algorithms is the rapidly exploring random tree or the RRT algorithm. And there has been several research about using the RRT algorithm for CPS testing purposes. The RRT algorithm is a sampling Monte Carlo algorithm which tries to bias search into the largest Voronoi regions of the search space, hence trying the robot to explore more of the unexplored regions. The algorithm shown here is a typical RRT algorithm which searches for a random point in the search space, finds the nearest node in the current tree, and then using this node, we steer for a very small amount of time, towards the random point. The tree gets formed as you would have seen in the GIF in the side. Let's start with the methodology. So as mentioned before, this is based on the RRT algorithm. We initialize the RRT tree from the starting position of the two cars. As mentioned before, we chose the objective space dimensions as the distance between the ego vehicle and the distance between the ego and the opponent vehicle and the ego completed percent. We convert the actual state space, which is a map space, to the objective space and initialize the tree with the start position as the root of the tree. We select a random point in the objective space and find the closest node of the current tree to it. This node in the objective space maps to a point in the map space. Now we have the nearest node. We simulate from the particular node by applying each of the possible perturbation to the operand for a fixed amount of time. We use two perturbations, which is increasing and decreasing the speed by 10%, and simulate for a small 10 time steps. The first image shows when the opponent went faster, and the second image shows when the opponent went slower. So this is different from the actual RRT algorithm as we showed in the motion planning, where we are just using one particular direction to move. Here we are simulating in all the possible perturbations that we have. Finally, when the simulation for the 10 time steps end, we project from the map space back to the nodes in our objective space. We create a new node from this new pose we received and add this node as the child node to the previously found nearest neighbor. We repeat this process until we iterate over a certain amount of nodes or reach a certain part of the track. Whenever a collision occurs, we mark it as such, and hence that node is used in the search for the nearest neighbor node. Hence that would be a leaf node then. Additionally, we show the clusters in the map to show which areas of the track most collisions are taking place at using the dbScan algorithm. We also provide a tool to retrace a collision so the tester can view the whole path from the beginning and check where and how the planner or the controller would have gone wrong. These are some sample images after using the DB scan algorithm to cluster the collisions. The reason to use a clustering algorithm is that we notice random testing may find a large number of failures, but they're sometimes very similar. For example, crashing on the first turn of the race. By clustering results in space, these do not get counted twice, and more information is available on the variety of faults that are found. As we can see the image above, the number of clusters found in the RRT based testing is way uh, is a lot more, and RRT based testing is able to find many more collisions ahead in the track in the second half part of the track. Also, note that spatial clustering contains parameters that require further tuning per application, and the method has two outputs: the number of clusters found and the number of outliers that do not belong to any cluster. Adding these two up, we compute the number of unique failures. Here we can see the results for a few planners we tested upon. We were able to detect over 3 to 4 times the collisions in the random strategy, even getting 110 times the collision in the second half of the track for the Frene planner. We find more collisions and unique crashes, which was defined just now, using the RT based strategy for all the controllers. The collisions in the second half of the track is much harder to find as we need successful trajectories to get to that point without colliding earlier. And we were able to find a large difference in the collisions for that using the RT based algorithm. Finally, even the standard deviation of the crash positions in the map space was much higher in the case of an RT based strategy. Thank you.